Welcome students. Now we are going to see concept of homeomorphism, but before that we are going to see now this definition. Now definition of open map here. Open map. So definition is that let xd and y row be metric spaces. A mapping f from x to y is said to be open if f of g is open in y whenever now we have this one, that is whenever g is open in x. It means that here now f carries open sets to open set here. So we write here that is f carries open sets in x, open sets in x to open in y. Now remember one more thing, that open sets need not be continuous. Open mapping need not be continuous here. So if you consider this now I is the mapping, that is identity map here. I is the mapping from metric space Ru, that is R with usual metric, and Rd is the discrete metric, R with discrete metric. Now here, now in this case, now this map is not continuous because we don't know that here if you take now singleton set, now this is suppose now S1x, now inverse image of this set now under this function is singleton here. Okay, so in this case, okay, inverse image of this singleton set is again singleton set here. Now this set is open here, but now this set is not open in this set because we know that singleton sets are closed in the usual metric space Ru here. So remember that now open map need not be continuous here. So this is the example of that one. Now next is the definition of homeomorphism here. So actually homeomorphism is also a function, okay, or also a map, okay, which is bijective, then which is continuous, and its inverse is also continuous. Now since f is bijective, so therefore we can say that its inverse exists. So now we are going to see definition of homeomorphism. Now definition homeomorphism. Now definition is that now let xd and y row be metric spaces, then we write here a mapping now f from x to y, that is from the set x to y is said to be or a function, okay, or a function is said to be a homeomorphism if okay, first one is that it should be injective. So if f is injective here, that is we write here f is injective and it is surjective, so we can write here f is bijective here. Okay, if f is bijective, then second is that f is continuous. Now function f is continuous Okay, third one is that now this map F inverse. Now F inverse exists because we know that F is bijective here. So since F is bijective, so we write here F inverse map from y to x, or F inverse is the inverse function of this. So we write here F inverse from y to x, and here now this is the third condition. So F inverse is continuous. So when we have this type of, now these three conditions, that is when F is bijective, F is continuous, F inverse is continuous, then the map F from x to y is said to be a homeomorphism, and we say that the spaces x and y are homeomorphic here. Okay, so we write here, if a homeomorphism from x to y exist, we say that the spaces x and y are homeomorphic. X and y are homeomorphic. For example, now consider this one. Okay, now here I am taking now this set. Okay, close bounded interval 0 to 1, and second one is now close bounded interval 0 to 2 with the visual metric here. Okay, now here, now in this case, if you take now f of x is equal to 2x, then f is a homeomorphism. Okay, then f is a homeomorphism of close interval 0 to 1 onto close bounded interval 0 to 2 here. So remember here, now in this case, now this is the homomorphism. Suppose if you take now x is equal to now close bounded interval, now this one, and y is equal to now close bounded interval 0 to 2. So here we write here f from x to y, where we have now f of x is equal to now this formula. Now this function is 1 1 on 2, that is bijective, then f is continuous, in its inverse function is also continuous here. So therefore now f is homeomorphism from close bounded interval 0 to 1 on to close bounded interval 0 to 2 here. Now remember that here one more thing is that now if you take now this map here, now this map, okay, here I am taking R with visual metric, that is RU, okay, and RD is the set R, that is set of real numbers with discrete metric. And if you take now this map I, okay, then remember now this is not homomorphism. Okay, so this is not homomorphism because we know that now singleton sets are here in this case open. Okay, and its inverse image under identity function here, now its inverse image is again singleton set here, but singletons are closed here. So here now in this case, now this function is not continuous. Okay, so therefore now these two faces are not homomorphic. So remember that R with visual metric and R with discrete metric are not homomorphic. Now next one is the theorem here. Now next theorem is about now homomorphism and the open sets here, so and closed sets. So we write here now theorem let xd and y row be metric spaces and f be function from x to y be a bijective function, here, that is this function is 1 1 and on 2. Then the following are equivalent. Then the following statements are equivalent. So first statement is that here F is homeomorphism. F is here homeomorphism. Then second one is this: the set G, which is subset of X, is open if and only if its image that is f of G, okay, which is contained in Y, is open here. And third statement is that the set, now here we are taking F, which is the subset of X, which is closed here, is closed. The set F of X is closed if and only if now its image f of F is contained in Y, is closed, okay, that its image which is contained in Y is closed. Now to prove this, now we are going to prove that here A implies B and B implies C here. So first one is that now here A implies B here. Now proof. Now statement A implies statement B. So it means that we have statement A, that is F is homomorphism. So we write here let. Now statement A here hold. Now since F is homomorphism, it means that F is bijective, F is continuous, F inverse is also continuous. Okay, so we write here then F and F inverse both are continuous here. Both are continuous. Now we want to show that when G is open in X, then its image is that is F of G is open in Y here. Now we take this set G. So let G, which is subset of X, be open. Okay, then by using continuity of F inverse here, so by continuity of F inverse, we write here F inverse, okay, inverse image of this set under F inverse is open in Y here, is open in Y. So this proves that now actually F of G, now this set is open in Y, because we know that here F inverse of G, okay, or inverse image of G under function F inverse is F of G here. So F of G is open in Y, okay, when we have G is open in X here. Now for the converse part, okay, when F of G is open in Y, then we are going to show that G is open in X here. Now further, let F of G be open in Y. Okay, then by continuity of F, we write here F inverse of F of G is open in X, here. Okay, but F inverse of F of G is equal to V of G, because we know that function f is injective here. So we write here, since f is injective here, so we write this because function f is 1 to 1. So hence now f inverse of f of g is open in x. So but f inverse of f of g is g, hence g is open in x here. Now B implies C here. Now we have here statement B. Okay, B statement B, it means that the set G is open in X if and only if its image f of G is open in Y. Now here now to prove C, first we take f as a closed subset of X here, then we are going to show that here now its image f of f is closed in Y here. So we write here, let f be closed, okay, f be subset of X, be closed. Okay, then we write here its complement, then its complement is open in X, is open in X. Now by using statement B here, we write here by using B, yes, we write here now image of this set is open, okay, that is image of complement of f is open in Y here. Okay, but remember here, now here f and f complement are disjoint, okay, and here function f is 1 1 and on 2. So f of f, now this set is the complement of now this set, that is f of complement of f in Y, in Y. Now we know that now this set is open in Y, so we write here hence now f of f is closed set or closed in Y here, in Y. Now next is that when f of f is closed in Y, then we are going to prove that now this set f is closed in X here. So further let we write here f of f, that is image of set f is this set 1 be closed in Y. Let f of f be closed in Y. Okay, then its complement, so we write here complement of f is open in Y, is open in Y. Okay, again using now statement of B, so again by B we write here now its inverse image, so f inverse of now complement of f is open in X here, that is inverse image of complement of f of f is open in X. But we know that actually inverse image of f is the complement of now this set f inverse of now complement of f here. Okay, now this set is open in X here, and actually f inverse f of f is the complement of this set in X. So we write here therefore now f inverse f of f, that is f here is closed in X. We write this because we know that f is injective and f inverse is also injective. So F inverse of F is equal to, we have F, and that set is closed in X here. So thank you.